examples or maybe say some go over some of the questions and some of the topics if you guys have any deeper questions you want to know. And if we don't have time, just go ahead as always, fill it in the questions inside the chat. And then at the end, they can send me the questions, and then I'll be more than happy to respond there if there's more details or if there's links or anything you guys might want to see. All right, so with that, I'll get started. Yeah, so as I mentioned earlier, my name is Robert Loredo. I am the CEO and founder of Entangled Solutions Group. Basically, the company is what we do is we work in both AI, quantum, in both from a enablement and education perspective. So getting people started, understanding what it is, what are the potentials, what kind of strategies should, whether it be an industry or a university or government entities that are looking to get into quantum, what are the different areas they can get into, how to get started, how to build a team, what kind of use cases, as we're going to discuss here, should they be looking at and are ideal. And of course, formerly for the last 21 years, I've worked at IBM. The last 7 years of which I led the IBM Quantum Ambassador team, which is basically kind of what we're doing here, teaching a whole bunch of folks there on education and enablement on quantum computing, the effects, the potentials there are from industry as well as from the technology. And then prior to that, I worked on the Watson Group in AI for about over 10 years now, for some basically with AI, and then I was a master inventor. I have about 275 or so or more probably by now, patents in various different areas like quantum, AI, finance, etc. All right, but enough about me. You guys aren't really here to hear too much about me, just more about quantum use cases. So the way I want to actually run this, at least the slides that I kind of pulled out here for us to follow through, is to see a couple of things on just how quantum computing is transforming technology. Even though we don't yet have a real world use case that is highlighting a lot of the potential that quantum computing has, but it is transforming a lot of that work now because of the fact that learning quantum computing isn't like learning a new module or some new programming language that exists, because there's a lot of foundation when you do. Every programming language you learn is based on bits, right? Whereas now with quantum, you're talking about a qubit. So there's a different way of thinking about it. So this transformation takes some time, right? There's some barriers you have to kind of knock out. And once you do, then once you understand and educate yourself on what quantum is and what the algorithms do and how it's different from classical computing, then the next step is, all right, now how do I apply it? How do I look at the right use? What are good use cases for? What are good problems for quantum computing? And in what industries, what technologies, what kind of transformations can we do? And today's discussion will be technical, but of course, this can even be for executives. If you yourself are thinking about having a startup, or you have a startup, or you're an investor in companies, how do you know which ones have the right potential? How do you detect that degree and what the feasibility is? Can they reach that potential? And if so, how long will it take? Right. So this is all sort of what we want to kind of look into. And of course, the relevance on everything with regards to that transformation, right? So when you look at it, everybody's talking about, quantum is the big game-changing technology, which it could. I mean, it shows a lot of potential, has a lot of examples now, but there's a lot of work to get there. So there is still a lot of work around the algorithms. There's a lot of work around the implementation, integration with classical systems. You might have heard things like quantum-centric computing, which is putting a quantum computer, working with a high performance computing system or very large data center, computing very, very large problems, right? And these are done in academia. They're used a lot in the industry, right? So a lot of the stuff that you work on is done in these very, very large systems and requires a lot of processing power. So how do you go about offloading those kind of problems, right? So that transformation and the relevance that it has to that particular existing application technology is very important. The use cases we'll kind of go over here. Basically, I'm going to stick with some of the use cases that have a lot of areas where you can look into. I didn't want to look at anything too specific because I didn't want to pigeonhole you to something that's only available in this area with this machine. So this is very generic, very open. So I figured the areas will be finance, AI, life sciences, which includes chemistry, energy, and of course, supply chain, these things like optimization. Now, a couple of fundamentals before we get started. Quantum computing, of course, uses, as I mentioned earlier, quantum bits or qubits as they're known. So these enable certain problems to be solved that are various different. So don't think of quantum computing as, oh, it's another thing we can just pick up everything from classic and move it to a quantum system. It's not a lift and shift. It's it's very specific. An easy way to think about it is how do you basically do now, how do you work now with GPUs? So before GPUs, we were just using CPUs, right? Your classical systems bits, and it's a processor, multi-core processors, et cetera, parallel processing, all of these things we did, but those were with bits. Then you CPUs, and then you had a GPU come in, a graphic processing unit. Initially, that's what specifically those were created for. Graphic processing units are for creating images. They were back early days, or for gaming. It had better rendering, better images, and flows of video streaming, and all these things. So it it applied to a lot of that. But then somebody looked at it and took a deeper dive into the technology and realized, well, where else we can use this is we can use it for Bitcoin mining. So because it does a lot of good mathematical computation. So they applied it to that, and then all of a sudden, every Bitcoin miner is buying stacks and stacks and stacks of these GPUs so they could mine for Bitcoin, right? And then just after that, they said, well, what else you could compute with this? Machine learning models. So they used it for that. And now that's all you hear about now is GPUs and machine learning models. So quantum computing just extends that by you now have a CPU, a GPU, and now you're going to have a QPU, right? So understanding those particular fundamentals is important. There's a lot of things that go into that. I'm not going to go into all these in detail because most of this you probably either already know or there's so much information right now on learning it. But I just listed it here for you to all kind of understand what the different properties and principles there are in quantum computing to be aware of. Things like superposition, entanglement, and pretty much what are the limitations in classical systems in which quantum computing has. And like I said, there's a lot of stuff around this, but I wanted to include this here just so you guys can be aware of it. So the contextual background here, particularly for industry summary. So there's a lot of innovation that's going into a lot of quantum right now for years now. I mean, ever since I joined the quantum team back in 2018 as an ambassador, they already had a lot of companies working with IBM, particularly there because they made their systems open and available to everybody, right? They had a very large ecosystem that's growing. So a lot of early companies like JP Morgan Chase and a lot of industry, ExxonMobil, started working in because they had their researchers that knew quantum, and then you had these industry experts that knew the problems and the computations that happen in these industries. So putting the two together, they shared knowledge, right? And that's very important. That's pretty much what Qiskit Fall Fest is about. How do we get together and share this knowledge, right? How do we address, what kind of problems are unique? What kind of problems are unique to quantum computing, right? Where these challenges. So they drove a lot of that early trailblazing type of experimentation and learning from both what does work and what doesn't work. What has the potential? What can we do in the next 1 to 5 years versus what do we need 5 to 10 years because we need a very large system. So a lot of that goes in, and of course, in all the different industries that came in, like life sciences, energy, supply chain, and so forth and so on, started coming in and looking at the same computational potentials here. So to look at the industries in this case, so one aspect you have is there's certain types of problems that are good. So optimization problems, chemistry problems, right? Those are very what they call quantum easy problems, and not to be easy mean it's a simple way to follow a solution. Meaning there are use cases there that are very good to or align very well with the computational principles that exist in quantum chemistry, for example, physics, those kind of things. Anything anything you can kind of create and any problem you could find that you can convert into a Hamiltonian, for example, is a good use case for quantum. Particularly also within life sciences, some of those kind of same problems can apply to finance, right? Looking at risk management and these sort of algorithms that look at optimization problems, looking for hidden patterns or sort of things that you're looking at. So that's where finance comes in. So from the chemistry pieces in life sciences, looking at things for like drug discovery and quantum simulations of molecular structures, you can expand out into finance. And of course, the context that you learn and expand in those particular pieces can feed to and from AI as well. From quantum and AI, usually people bubble that into one topic, but it's actually, if you think about it, there's actually two directional topics. There's quantum for AI, which means you have quantum algorithms that help the current classical AI systems. Like, for example, classically, you have support vector machines. In quantum, you have quantum support vector machines, quantum neural networks, and these sort of things, right? So that's the quantum for AI. The other way around is also have AI for quantum. Right? So this is sort of things like the Qiskit code assistant, right? It's an AI system that helps a quantum developers, quantum researchers to be able to, bootstrap or work on their particular algorithms and structure their code. Because the assistant, the Qiskit assistant particularly, is very aware of not just understanding quantum algorithms, but also understanding a lot of the intricacies. What about error correction, error mitigation, error suppression? What about connecting with the right hardware? What do you, how do you map those problems? How do you optimize that circuit? So there's a lot of things in there that AI for quantum can also provide, right? So there's a lot of potentials in those aspects. Energy and supply chain efficiency, these are very sort of optimization problems to some point, but they're very important. As what you hear in the news now, with particularly with all the GPUs and AI that's growing around the world, there's a lot of energy consumption with a lot of these systems, right? And the more the GPUs that you need, your application needs, the more energy it's going to need. And it means that in order to, once we peak up at hit these peaks on these energy, it then becomes, well, where do we take the energy from if we don't have any more to produce, right? So it can become a very big problem very quickly. So one of the aspects of this is to see, well, how do we offload a lot of that heavy computation to a quantum system and make it better in a sense, right? So looking at some examples here, you have obviously optimizing the power management using real-time data analysis, looking for anomaly detections or better routes or better optimization of power, particularly when you have surges or certain particular aspects of those. In fact, there's a very interesting startup that came up about 2 or 3 weeks ago. I read about it called Emerald AI. Highly recommend reading up on them if you haven't. The CEO and starter of that company actually did a TEDx recently as well too, where he describes sort of way where they tested this thing on a very in the middle of the desert on peak time in the summer to see a data center running and pulling all this stuff. How do we, using software, make that more efficient, right? So grid and logistics are around that as well. So the logistics, of course, is also something else. How do you move products around, move things around? Right now, with Amazon and eBay and all these things, and people buying and selling stuff online, or and even ordering things online, you have all these little robots rolling around now. How do you make that very efficient? What about the logistics around that? How can you best send a product from point A to point B effectively and efficiently, right? So logistics very important there. And there's, of course, other challenges that you look for here. And one of them, of course, is workforce development. I could create an algorithm that solves all this problem, but then who's going to be the one that's going to go out there and implement it, right? Who's actually executing all these things, right? There's one thing to talk about, hardware. You're talking about the software. You're talking about the problems you're trying to solve and all these things. But great, but now who's going to do the installation? Who's going to actually do the running? Who's going to maintain this system? Who's going to look for the next step? Who's going to do those? Look to see, okay, once this goes into production, everything works great in a research, but when you put it in a research lab or in some contained area, but once you put something in production, then you have human factors to gets involved in everything else. So there's a lot of challenges that are also still out there that are not necessarily specific to quantum algorithms. So to dive a little bit in each one of these, again, I'm mostly posting these to give you guys an idea as to what there is in there. But finance, I mentioned, right? There's various different advancements on it. Early stuff you can read about are like portfolio optimization, risk management, fraud detection, and getting more hyper accurate results. There's things like Monte Carlo estimations that were optimized here. They get some kind of quadratic optimization there with respect to getting more accurate results with not many samples, for example. So there's a lot of papers, a lot of research out there. Again, one part is understanding those pieces, which is the education part. You read a paper, you understand it, that's great. Then the second part is the enablement. How do you go about applying it? Now you have to think about where else can I apply this type of solution? And those are basically how these problems kind of start expanding on their own in that aspect. Portfolio optimization, of course, there's actually a great paper that came up about maybe 2018, 2019. It's been a few years now that did some early work around optimization, European option pricing, and these sort of things. So if finance is your thing, there's definitely a lot of work around this, particularly very early on. And even now, they're looking at optimization and hidden patterns within certain components, right? Because to get optimization, you're looking, the more data you have, the more accurate you get your systems, but then that means you have to have a very, very large system. So how do you optimize a lot of that? Whether it's ingesting the data and analyzing it or looking and determining what the next best step is, or in this case, what's the best stocks to buy or sell or call or put, et cetera, right? So a lot of work around there. As I mentioned earlier, fraud detection is very, very important. It's a very important and a very costly a problem that's out there. I mean, if you think about it, it's a multi-trillion-dollar problem. So if you could if you could shave off 1% of that off of the current problems that are, let's say, like detecting some kind of fraud or some kind of any kind of fraudulent activity, then if I could take 1% off of a multi-trillion dollar product, that 1% is multi-billion dollar problem you just solved a lot of people, right? So So those, even though it might seem like a small increment in whether it's identification or analysis, it's very important and is very costly, right? So it's a very high value type of problem you should look into. So there's a lot of quantum machine learning algorithms and advancements that are working on this as well. Then quantum enhanced, as I mentioned before. How does the AI capabilities, how do you transform those capabilities into something that a quantum researcher or quantum, think of somebody in IT staff somewhere trying to implement a lot of what you're building. There's a lot of work that goes in there, when you're talking about neural networks, but yeah, but I got to run this thing. How am I going to offload it? How do I know how it's going to affect the current system that we're on, right? So there's a lot of AI and looking for patterns about certain things that maybe you can learn from this, right? So this quantum enhanced machine learning applies not only for optimizing the machine learning models in classical systems, but also think about users, right? Use cases and these sort of things. Neural networks, very important. There's a lot of this work going on, particularly in the life sciences, even in some other areas like image processing. You look at neural networks, there's a lot of different components to that. You have quantum neural networks, quantum convolution neural networks. So there's a lot of there's a bunch of new papers that really actually came out. I have backlisted on my list of reading materials that really cover some of the new aspects of looking at this. And of course, they involves a lot of large data sets. So even part of this is just because you don't, let's say you're assuming a neural network and each neuron is each layer represents some component of a quantum system, whether it be a qubit or a set of qubits. How do if I have thousands and thousands of parameters, then does that mean I need thousands and thousands of qubits? If I do, then my solution is not going to be ready for years because we don't have thousands and thousands of qubits yet. But how do you basically reduce that so that you're offloading just enough to get enough of it, and then you can scale it up as the system goes? Can you get that problem or reduce it down to like 120 or 150 qubits so you can run it on the best of the best machines out there that can run those? You get some results. You can then check and see, okay, is the error mitigation there? How do you verify those things? Because once you start to scale those into, thousands of qubits and, hundreds of thousands, not billions of operations deep, so you have this very wide and very deep circuit, width being the number of qubits and depth being the number of operations or gates. How do you verify that? How do you validate the result once it goes beyond a particular size that existing classical verifications and solutions aren't existing, right? So a lot of that goes into these machine learning models and machine learning applications, right? Life sciences, of course, is very, very popular with these, particularly when you're talking about enhancing drug discovery, everything from looking at target bindings and all of these things in the early development phases, right? If you think about it, right now there's a catalog of different molecular structures that are used for a lot of these early stage drug discovery experiments and research. And their limitation is because we can understand them because we can simulate them on classical systems. But to get the very specificity and to get the exact almost operations it's not really that set up, right? So we know what it was. It's almost like this is good enough for as far as our computations go. But to be able to increase that will take a lot more resources out of classical systems. So there are people currently now optimizing algorithms or optimizing how we discover these components to maybe be able to do these large systems. And at the same time, you have these quantum applications or quantum algorithms that are expanding the understanding of or at least the molecular structures, or getting more hyper accurate results as far as how multiple molecules and atoms react to each other, right? So all of these things are very much being worked on now, and there's a lot of applications that can benefit from these. Even within AI, I mean, there's a lot of AI folks that are looking at how do we optimize clinical trials, right? How do you determine the best patient for a particular problem, et cetera. So all of those really kind of build into those. Genomics data, of course, just another large amount of data that you need to look into. You're looking at billions and billions of pairs that are connected to in a body, and of course, everybody's different. So you have some people are allergic to certain things. Some people take medicines, and there's different side effects you get. How many times you've seen a commercial for some medication, and then half the commercial is basically all the side effects that medicine does. Of course, it's that way. They have to do that because when they've done those trials, they realize, well, some folks get headaches, nausea, and that's whatever else they have listed in those side effects because This is what happens when they take this medication. Some bodies react differently to the others. But if you're able to basically come down and understand the specifics about the how your body works, right? It's sort of personalized medicine, meaning that it's going to be personalized based on your structure, your DNA, and everything else, and how it will react to these particular types of medications. Then they can if maybe effectively analyze that information and blend them in a certain way, or create them, I should say, blend them in, but blends in with your body, I should say, better, so that one, it reduces the number of side effects, because those side effects caused because maybe the particular way that molecular structure that's carrying the antivirus, let's say, is attacking the bad cells. It might also be aligned with to attack the good cells. So this is why things like you lose your hair, for example, when you're taking chemotherapy, because it's killing every living cell, or rather every reproducing cell you have. So there's a lot of different things that you can that go into this, and of course, a lot of that requires a lot of computation. So personalized medicine, genomic data analysis, very, very large. So moving to grid management optimization. So when if you live on the grid, which most of us do, right, this energy grid, we don't see is that there's a lot of computation happening here while you're sitting at home or in the office or even while you're driving down the street. All the power signs or the stoplights and all the lights, street lights that you have, whether the power in your house, the power in the restaurant you're going to go see, or in your office buildings, on planes, on the airports, all these things, all that is managed somehow, right? There's got to be some power going out there, and of course, there's events that happen that might disrupt a lot of that. Everything from simple as a branch from somebody's house landing on a power line, and it creates a short circuits on the fuse, and now somebody's got to get called to go out and replace the fuse. So until somebody does, you're sitting there without power, which is a problem if you have an important phone call to happen. Like for example, like if I had a power spike and have to wait for a company, I wouldn't be able to join here, or at least not via my system. I can join on my phone, thankfully. But those are the kind of events that can happen. So managing and optimizing those particular pieces is very important. How do you optimize when something is broken? How do you optimize when you have a storm? I live here in Florida. We have hurricanes here 6 months out of the year. So how do you prepare before, during, and after the hurricane? And not just energy, but other things as well, the logistics and all that comes with it. So all of that is very important. Battery materials, of course, affects a lot of that as well. Right now, you have not only your wireless, chargers and your phones that you have to charge, but you can charge something as large as your car, trucks, these little robots you see rolling around the street delivering things. All those use batteries, and all of them need to be recharged, right? So, what makes this difficult with, at least for power grid management, is that while there's going to be certain spikes in certain areas where these battery chargers are going to spike up because a lot of people are plugging in and using the systems. Usually that's at night when people are home because they drive their cars, electric cars, they go home. Those that have a home charger, they'll plug it in overnight. When they wake up in the morning, it's fully charged. So in the evening, you'll actually get a power spike, where normally powers in the evening is kind of minimal because there's no sun, there's no hot, so the ACs and the fans and the lights are off and not working. But now you have this big power charger spiking up to charge a large battery. So how do you do the simulations to come up with better battery materials? How do you make it so that the battery doesn't need a full night or a bunch of hours to charge? You could just do it very quickly, or maybe increasing the capacity on a battery so that once it's fully charged, it can run 10 times longer than the regular batteries that are now. And there's a lot of papers and things written on the different types of batteries that different companies are looking into. Right. So those are just some good examples as to sort of just the type of problems that there are. But again, it doesn't mean that, okay, there's battery problems means it's not working, or it may not work for a while, or it's not my area of expertise, so I'm not really interested in those. That doesn't necessarily mean that there aren't any opportunities or challenges in adopting quantum in any industry or any academia, right? So you got to look at it from a perspective of first understanding how quantum is used, what are good problems, where we are now with respect to quantum, not just on the hardware, but look at the algorithms, look at implementation. There was a paper, rather. There was announcements recently by both HSBC and by Vanguard, where they're using quantum computing. They've actually plugged it into a production environment to get some information to try things out, in a sense, right? So they're already taking that early step of going, well, let's plug it in and see how it works. How do we get it to plug in, right? Even if it doesn't work, or if it's working, but it's not producing anything that's going to really revolutionize everything just yet. that's not that wasn't the goal. The goal there is, well, can we do this? How do we what are the challenges? What do we need to consider? What are the things that we have to make sure in place? Obviously, when you're in an industry like finance or healthcare or anything else, energy, there's a lot of regulations and compliances, right? There's you have to the system has to work. You can't just rely on it and plug it in and say, well, something else we'll figure out how it as it goes. You have to have contingency plans, mitigations, and all these sort of things, right? Verification, validation. There's a lot of stuff that has to go into that has nothing to do with the algorithm specifically or the hardware. It's really more of just, well, if you want to put it in production, here's a long list of stuff you got to think about, right? So all that transformative opportunities, all in all different sectors, they all require some kind of. They're going to have some challenges. There might be some limitations. There might be some, and you can see here where I wrote there, talent shortages, which is very important. I mean, I think I read about 2 or 3 articles where it discusses that. I think of all the job openings that are available in quantum, I think only 33% can be filled with the right skill sets, right? People that have the skills to be able to do this. So those are all important again. And again, the last point I put there is very important because collaboration is essential. It's very early on right now. Um, that's why you have events like this, like Qiskit Fall Fest and everything else that you can everywhere else you can find, hackathons and things happening around. The collaboration is very essential. One, it helps you understand from others because I always, I still play guitar. I learned from another musician that he basically says he learned most of his really good chops and skills watching others play. Right. So that's the one thing the same here is if you play with others in quantum, you're going to learn something, you're going to hear something, you're going to see maybe people thinking things differently, or they may even learn from you, right? So that collaboration is very essential because it helps one expand because you might be too focused on one particular problem or one particular type of thing that you're trying to solve. But then when you broaden out your horizons in this sense and look at how others were using it, what the thinking process is there, that's also very important. So I definitely want to leave you with those particular thoughts in mind with that. So with that, I will open up for any questions. I'll stop sharing here and see if you guys have any questions on anything that I talked about or any questions you have that might not be on this topic. And in the meantime, while you guys are thinking, I'm going to look through the chat here to see if there's anything here.
We have some question for the chat. Okay. The first one is how those exactly works. Quantum constants with
neural networks. Okay. So there's so I guess it depends on the level of where you're asking the question here, right? So the question is how does that exactly work? Quantum constants with neural networks. So first, I'm assuming you understand the concept of a qubit, right? Superposition, entanglement, interference, right? Those quantum computational principles there, right? So with neural networks, it depends on how you want to implement or what advantages you want to see. So I'll give you a simple example that I remember we had in the original Qiskit textbook years ago, where the implementation had qubits representing the individual nodes on a hidden layer, right? So every node that you have in that hidden layer was a qubit, right? And depending on that particular setting you get, you adjust that qubit to that particular value, right? So as you go through each layer, let's say you have 10 layers, and then you're going to have 5 layers and 2 layers, right? Then you have your autoencoder and blah, blah, blah. So if you have 5 layers, you have, okay, 5 qubits, right? So each qubit, it represents that particular node. So that would adjust however way you need it, right? And then you would do that same thing with the next layer, next layer. So if you have 5 qubits on the first one, then you can go and get, let's say 3 qubits, 2 qubits, etc. Right? So to run one layer like this, you'll need 5 plus 3 plus 2, so you'll need 10 qubits, right? So that was one of the early stages. So it all really kind of depends on. Again, this goes back to the question. The question is actually the answer is in that aspect, right? First, you have to understand the quantum computation principles. So you can understand what can you and can't you do with a quantum system, quantum qubits, and rather qubits, etc. And then once you know, how do I apply it? In this case, it's how does a qubit work? How does a quantum system work? How do I apply it to a neural network, right? And that application process, that's where all the algorithm development and optimization problems and all these things kind of work, because now it's up to you to figure out, all right, I understand how this works. How does it work? A good example is this, at least a real world example is this, right? Somebody invented the car many, many years ago, right? They had, okay, your car has what, four wheels, your little steering wheel, you had to walk to the front and crank it just to get it started. It would sputter, you'd get on, and then you drive, and then the brake was just a little lever because it was always going to run. The brake determined the brake was the brake and the accelerator at the same time, right? Very, very rudimentary, right? And not many, most of people were used to walking or riding their horses and horse and buggies. So you had the early cars, they were very small, so they fit two people, and then the later car with two people in the front and two people in the back, and that was it. But people were, carrying materials and farmers, and they're like, well, I can't use this thing. It doesn't work for me. So somebody understood, well, this is how you build a car. Now I want to build this a vehicle for a farmer. They carry a lot of materials, like, their farm equipment. So now comes the development of the truck, right? Et cetera, et cetera. So again, this is sort of, if you understand the fundamental concepts of a vehicle in this sense, right? You need an engine, you need brakes, you need accelerator, it needs power, right? If I'm going to carry these things, I can't use the same engine. I got to make a stronger engine, right? So you understand the fundamentals, and then you look for that use case, that problem you're trying to solve. So, well, a car would be great for a farmer, but there's not this car because it's too small. So I need to do something and enhance this in this way. So we need to build this and build up on top. It still uses it. If you look at any truck, it has tires, it has an engine, it has brakes, it has an accelerator, right? But now you have just a different type of vehicle, right? So that, I hope that helps in that aspect.
Okay,
Let's
wonderful. We had another question for Tabitha. What have you found to be the best way to encourage and foster collaboration across disciplines, especially between current and networking world and the quantum community?
That's a good question. So that's also one of the reasons why I started my company, is that there's a lot of folks that want to get into quantum. They want to collaborate. Of course, the ecosystem is large yet small, right? The Qiskit ecosystem, for example, is the largest in the world, right? You could throw a rock in any country and it's going to hit somebody. That's trying at least quantum. So, but the challenge, I guess, in this sense is I want to work with somebody both that is either at my level or better, because, or even not at your level, just at a different level, so that either you can learn or you can teach, right? So you can do either one. But at the same time, you want to find a problem that you can, let me move this window some way. So you find you want to also work together so you can collaborate and learn from each other to build something that might be innovative or new. Maybe even you can patent something, or you can publish something, or just create something and use that as something to start with. The best ways I find to do that are two different ways to do this. One is events like this, hackathons, fall fest, all these things, because this is where you find, as you went for this fall fest, they had a whole big table of where you can put in what types of problem you're interested in. You're a mentee or you're a mentor. What do you want to do? What do you want to work on? And then it will, obviously, people from around the world will see that and think, oh, here's an interesting problem, and then they'll apply, and then you get together and you can do it. So events like this is a great way to meet people, and of course, to meet people from all over the world. I'm mentoring two teams now, and they span every continent practically, right? So that's one way to, so basically go where the ecosystem, go where the people are. Now, when you talk about cross disciplines, that's actually an interesting thing. And that's also, I mentioned, with the reason I started the company was because a lot of folks are sort of like, okay, I'm just barely understanding my own industry in quantum. I can't think about what they're doing in aerospace. If my job is in life sciences, or I'm doing a degree and I'm studying in finance, why do I want to go all the way there and learn about logistics? Why do I have to learn about finance if I'm in life sciences or I'm in something else? You're not, what I recommend, or what I work with partners, is that you don't want to go in there and look at it as the whole industry, like, well, I have to go learn this. No. Your common bond with that other expert or that other person you're working with in that industry is the computations, right? I can work with anybody in the world in any industry, because the conversation I have is that common general thing that links the two, right? Which is what? Computing. We're talking about computing, right? It's the same way that CPUs and GPUs got together. Why do I gotta learn about gaming if my problem is in Bitcoin mining? Well, let's talk about the mathematical aspects. You could compute this on a GPU much faster than CPU. Oh, so I could mine for Bitcoin much faster and get a real much. Yeah. All right, let's do this. And boom, you got that going, right? Same thing with the AI models, CPU, GPU. Let's do this. Hey, what about, okay, we got Bitcoin mining done, we got gaming done. What about, learning models, or machine learning? So then they started collaborating on the computational aspects, right? And boom, now you have a whole other industry in there, right? So I would say for those, it's easier to be able to have that communication at that level, because you're talking about basic computation, which is what these two systems do, and classical and quantum, and now you're building everything from it. Now you can talk about other things. They say, okay, you computed this to solve that problem. If I have this problem, what's a good way to map this? How did you map the problem to that? How did you map this computation to that problem? Teach me how to do that, right? And that's kind of what you want to look at. And that's usually what I find is the easiest way to kind of really connect and collaborate in that aspect. It just starts with something easy rather than having to explain to you what the problem is I'm trying to solve, which you don't need to know. You just need to know is how am I computing, how am I using a QPU to set up this problem, right? So I hope that helps.
We had another question. In what industry do you expect to see the fastest adoption of quantum computing in the next 3 or 5 years?
That's actually interesting because initially the thought was it would be chemistry first, then machine learning, and then optimization. And that basically is because, we figure, well, a lot of the classical solvers we have are very, very good. But over the last year or two, there were some algorithm developments that actually now flipped a couple of those. So it's still chemistry and life sciences and these sort of things, drug discovery at the base. But because of some of the computational updates and algorithm discoveries that have been happening, the machine learning and optimization is in a sense sort of flipped because looking at hidden patterns and optimization components, particularly these new algorithms that are the SQD and these sort of things, they're looking at easier ways to apply because those algorithms are written for systems that are now, which are not at these large scale systems. They figure, well, we can use quantum not for the whole computation, but for part of it. But the part that it does, it takes up a lot of the steps here that we need to do. So it comes in for a little bit, provides some updates, come back, and then the classical system will take over. And it just takes over and does something different, right? So I think with those, it would definitely be chemistry, anything chemistry or physics, right? So it could be life sciences, it could be battery material design, all of those sort of things that have to do with chemical acids, things with corrosion, all of those kind of aspects. You can look at maybe lighter materials. So in aviation, aerospace, and defense, you have lighter materials, right? So you can create a plane that's lighter because the material is much stronger, but yet thinner, not as heavy, right? Chemical design, so maybe better fuels and all these things. And that, of course, leads to energy as well, right? And then the second one will be optimization problems. And everything is an optimization problem, right? Even machine learning is an optimization problem, right? How do I optimize? How do I get better results from all this data without having to use all the data? Can I do it with a quadratic amount of data? So if I said about having 1,000 parameters that I need, can I get the same accuracy with just 100? Right. So a lot of those types of problems, I think, are the ones that'll be the ones. And of course, the industries just follow those computations. If I find a good optimization problem that solves something, then there's other industries that use those particular types of computation as part of their algorithm development or computation, and that will benefit from that as well, right? And the value depends on what it is. Like I mentioned, if in finance, for example, if I solve 1% of a problem that's a small problem, like, well, okay, we can move products from a port 1% faster. Okay, that's fine. We have some reduction. And that solves, if it's a multi-million or multi-billion dollar industry, okay, 1% is still big. But if you go to finance and you do the same optimization, but you solve it things like I mentioned earlier, fraud detection, which is over $1 trillion problem, that's a bigger value to that, right? It's 1% of what trillion is bigger than 1% of a few billion, right? So it all just kind of depends on what it is. But I think the industries will just align to those types of problems that are solved from those algorithms. So life sciences, chemistry, and anything like optimization will be the ones I see there. Okay, let's see. And I think don't see any other. At least I don't see any other questions in the chat. And I think.
Hi, Doctor.
Yeah.
Have another question.
Sure.
What do you think are the biggest roadblocks to integrating quantum computing into your current infrastructure to create a cohesive system?
Yeah, so the integration is actually a lot of the work that's being done by most of the research now. If you look at now, if I Qiskit, the latest version 2.0, and actually 2.1 now, I think we're up to 2.2. A lot of that has to do with that orchestration, right? Or combining with HPC systems, for example. For 2.0, they went for 1.0 was mostly performance updates, right? Get things to run better, the Qiskit runtime, and all these things. Now for 2.0, it's on just this. How do we best integrate and increase the performance of, and like you mentioned, the cohesion and orchestration between these classical systems, particularly like if you think about it, like high performance computing systems, right? Those are very large systems. They're very, very, very delicate. And maybe delicate, like if, every nanosecond or millisecond is an eternity because they're just very, very fast systems, right? So if you're going to offload something like that to a quantum system, how do you do that most efficiently and effectively? Meaning, yeah, I want to do it. It might cost me a few seconds, but I'm going to either reduce the amount of power that I normally would need to solve this a problem this size, or I'm going to get much more hyper accurate results so that I don't need to as much samples in order to solve this particular problem. Right? Many different ways of reducing the cost, the overall cost of running something purely on a classical system. A lot of orchestration, though, involves integrating with these systems. And as we know, if any of us you hear on a call that work on HPC, you know that a lot of that code is written in C or C++, right? And of course, Qiskit and Quantum are all written on Python because it started with computational scientists using it, and everybody used Python then. But now when we're trying to actually integrate it, a lot of that lower level, lower stage, integration components, they're now working to create a C API. And now you can integrate it with that. And of course, it's growing out now even much more different classes that they're introducing that helps that integration piece so that you can now code and not have to worry about dependencies and doing this whole porting of two different languages, which if for us developers know that's not an easy thing to do. And even a worse thing to try to maintain because you think of versions and things that change. So by putting these together, creating that cohesion, as you mentioned here, really helps because that helps blend everything together. It makes it easier for not only you, the algorithm developer, the application developer, but also that person that none of us really think about, but he's there. He's the person that's got to maintain the system, right? Whether he or she are sitting there and something goes wrong, they're going to get that phone call. Hey, my system's slow now. All of a sudden, what's going on? They have to go in and look and see what's going on. And if they can't understand it because it's something weird and quirky, it's not going to help, right? So tooling and these sort of things really will come into play in that aspect.
We had another question, Robert. So many universities in Latin America are just starting to introduce quantum computing. What steps can academics institution in the region take up to accelerate education and research in the field?
Yeah, so first off, if you're already studying in quantum, you're way ahead of the rest, right? And by that I mean there's I can't remember what the full quote is, but I remember the quote went something around like if you're starting on time, if you're starting early, you're starting on time. If you start like on time or today, you're starting late in a sense, right? And basically it's saying that the sooner the better, right? Because as you're seeing, a lot of folks are getting in and just getting started. Now, Latin America, particularly, I mean, Mexico and everywhere else, there's a huge ecosystem there. In fact, about a month ago, I was down in Uruguay at the University of Montevideo. They were hosting a huge hackathon, where they invited. They had a Hispanic Latin network there, and they invited folks from all different countries. I think they had overall 1,500 or 1,800 applicants, and they had to select 88 because it was a set size. So had everybody from Brazil, from Mexico, from Ecuador, from Peru, from Colombia, Argentina, Chile, everywhere. I mean, you can think of it, they were there, right? And they were all working same way. They had large teams. They got together, presented some really, really good ideas. Their focus was on climate, the environment. I was there as a judge. Every single one of those were incredible projects. So there's a lot of great activity, a lot of great work there. But to your question is, yes, I think there's definitely a lot of opportunities, one in Latin America for this. The beauty of it is that quantum is still democratized in a sense, right? We can all still have access to these systems. We have access to the software, the hardware. Well, some of the hardware, some of them open, some of them you have to apply and get, but there's some availability there, right? It's not this contained closed thing where it's in a lab and only select people are allowed in to use it for a few seconds. We're not there. I hope we don't. We're not going to be there for a long, long, long time. But I got to, right now, as far as access, programs like this, like Fall Fest, where we can just all learn and collaborate, that's really the key thing that's going to make sure that no one's left behind. I mean, my own personal rule is that I don't want to have everybody left behind with this thing. There's so much potential there. There's so much growth needed. I mean, like I mentioned, there was an article I read that has only 33% of the people that are in quantum that are skilled can actually fill only 33% of jobs that are out there. So there's not a limitation of jobs. I think just get out there, start learning, start experimenting. I remember one also thing came in mind, it's a very competitive area, right? There's 33% of jobs available, but they're not going to just pick whoever's coming in the door. It's not that bad, right? But they are going to want to know, they're going to pick, I mean, just put it, I always say this, my advice to everybody is always this. Just put yourself in the mind of, let's say you're creating your own startup and you're hiring people and you only have a budget, meaning you only have, let's say, $500,000 or $1 million, but you got to hire these 3, 4 people to be your experts that's going to basically implement what you're thinking. Now think about what your resume would look like in that aspect. Now I'm saying you don't have to be a PhD or anything. Of course, a lot of folks that are in there are PhDs, but they're running the very experimental. But you think about the entire landscape of the sort of jobs that are available for quantum or those quantum skills, right? Like I mentioned, if you're just managing or you're the admin of something, you have to learn something about it, right? So having quantum on your resume says a lot. But if others have quantum in their resume, then what's going to separate you from the others, right? What's spiking your resume to the top as here's an ideal candidate. Put that in your mind as you're learning these things and understanding and trying to figure out what to do. Do that, collaborate with others, try to figure things out, and then start looking at some of those jobs that are out there now. Look at the skills that they require. See the education level, what kind of projects, etc. So that will help you work on these projects. When you work on a project, just don't pick a random project. Oh, I like to work on, let me do that. That sounds fun. Great. But it's better if you find a project that's aligned with the kind of job you're looking for, those kind of skills, work on that kind of project or create that project, use that, and then when you finish that project can now go in your resume, right? So when they say I'm looking for somebody's skills in quantum neural networks, so you're gonna have someone say, yeah, I know what that is, versus yes, but your resume would say, I not only do I know what that is, if you go to this GitHub link, you can actually see what I did, what the team and I did, or what I specifically did, contributed to this work, right? That's a differentiator. That's what's going to get somebody to say, okay, we need to have this person. We need to have you in our company, right? So I would definitely keep that in mind as you're developing yourself through this. I'm doing that myself. I'm learning this. I'm not here as oh, I know what's going on. I've had a lot of experience, but I've had to learn all along the way. I'm still learning now. This is why I go to these conferences. This is why I go to these places here, because some people will ask questions and I'll think, oh, that's a good question. I never thought of that. And it forces me to go on and think, right? So all those things are definitely things that I would recommend everybody do here. So I hope that answers your question there.
Yeah, that's really good question. And last questions. That is completely resonant with the previous one. So, what kind of strategy you would recommend to help to retain and grow up the quantum talent in Latin America, rather than losing to more developed test region or countries?
Yeah. You mean talking about increasing like the workforce, or how do you mean?
Instead to go directly to the industry and USA, UK, could be the advice for those that want to create something consolidated in the art countries, in Latin America especially?
Yeah, that's a good point. Oh, yeah, that's a good question. So first, I would definitely say is work with those that want to work in quantum. What I mean is, universities. There's always a professor that's either interested or currently working on something in quantum. Those are the easy people to find because you can look at them either through the university web pages and just search for professors working on the word quantum. You could either look on Google Scholar, search for the university name plus quantum, and you'll see a whole lot of papers or something right on there. So that's one thing. That's one thing. That's one way you can find out, at least from academia, to see who's working on quantum, and then you can maybe start collaborating with them to get your foot in the door as far as, well, what's the next step? What are you working on that's kind of doing that for that next step, that research that you're looking for? Because most of the work that they get might also be coming from some grant, right, or some co-project they have with somebody in the industry, right? It could be either a grant coming from the government because they want you to look into material science or energy, or it could be a company that's collaborating with the university to say, look, for example, me, I have many projects that I want to build off the ground, and I want to start with these prototypes. So I would go to the universities and say, listen, who do you have that's good at programming, at this and this, and understands this? I want to use this as a capstone, so they could use it as a senior project or work together with the university, and then we could collaborate that way. Me from the industry helping the university kind of build this stuff out as a collaborative effort. So for the university, that's one aspect. Then you also have on the government side, right? Those governments that are giving off grants, right? If you go to like your local city or municipal chamber of commerce, right? These are basically other companies that are coming together. Walk around there, see who their members are, talk with them about quantum. Do they know what quantum is? You can maybe be their quantum expert. If they want to go to quantum, you want them to think of your name and they'll call you, right? That could build in some kind of component because maybe they are looking to get a quantum, they just have no idea. You can help them do that, right? So from government entities and that aspect and access to industry, look at conferences. When you go to conferences, any industry conferences that are nearby, attend those, see if there's any quantum presentations, or maybe if you're already working on something with the university, you could present at a conference, right? So those are good ways that you can kind of not only connect with those that are working on quantum, but if they're not and they're interested, you can come in as somebody who's also interested in quantum, and you can collaborate together as far as let's learn this together. Let's figure out what we can do, and then you can collaborate in that aspect. And I actually see some questions came in on the chats and Tabitha. So what are the biggest roadblocks of integrating? Oh, look, we covered that one. Oh, do you think quantum is going to present challenges to policy, regulations, governance, similar that we are currently seeing with AI? I mean, there's that could be an entire topic we can talk for an hour on, just when you think about ethics and responsibility of quantum of technologies, right? So there's always going to be some. I mean, obviously, of course, it depends on the industry and or the particular types of algorithms or computational aspects that you're building, right? If I'm doing something in finance, then I have financial regulations and compliance that, or at least not too much I have, but whoever I'm working with, that company or that bank, let's say, or that investment firm or what have you, they have certain, obviously policies and compliance and regulations that they have to follow. So it just becomes more of just for yourself as you're working in an industry, you should be aware of those policies and regulations, right? You got to understand what the governance are, what the rules are, what are the aspects you need to consider, what are the codes. I mean, you don't have to memorize what that code is in their code book, but at least understand what are the particular constraints, what specifically around quantum do they have that you need to think about. So all of those are very important. And then, of course, there's a whole responsibility and ethics, right? And that goes back to that's a responsibility that we all have, whether you're in technology or not, right? Ethical usage and these sort of things, right? Making sure that it's only being used for good. But there are, of course, very, very highly regulated areas, even with that aspect, right? This dual usage kind of things, right? Where we have one particular product that has a commercial usage, but may also have military or some other use for it, right? So, let's take nuclear as a good example. You create nuclear power, but you also create a nuclear bomb, right? So you have regulations and compliance and these sort of things and governance around how you do that and what to do. So with anything, I think for that one, I think there will always be some challenge, but the correct answer to that, I would say, is you should make it a point to make sure that you're aware of what those challenges are. Because if somebody's bringing you in as an expert on quantum, you want to make sure that you are not only expert in quantum, but also with anything else around that, the applications, the policies, regulation, governance, specifically in that industry that either the company that's hiring you or that you're working for, you want to make sure that you understand that just to be, responsible yourself. So I hope that helps in that response.
Thank you, Robert. It was a wonderful lecture. Thank you so much for accepting our invitation, especially for spreading your knowledge about the Latin America community, in particular Mexico. So thank you so much again.
Of course, thank you
We'll
very
see
much
you.
for the invitation. I wish you all luck. I hope to see you all write a book one day or present somewhere at a conference. If I do, definitely come by and say hi. Thank you very much. Yeah, guys, have a great day.
Thank you, Robert.
You